Okay, so today we are going to discuss this Zimmer Cocycle Super-rigidity. So let me try to state it. So for this we need to introduce a couple of notations and settings. So it is the other side of the spectrum from this Zimmer amenable reduction. So Zimmer amenable reduction was about action by amenable groups, and it gave a reasonably nice descriptions of how the cocycles look like. Now we are going to talk about semi-simple Lie groups. So actually we are just concentrating on SLNR, which is a very non-amenable group, so that's why I'm saying it's the other end of the spectrum. And we will see what it is. So we take now G equals to SLNR, n at least 3, so it really goes back to the spirit of this normal subgroup theorem, where the n has to be at least 3. We take gamma lattice, we make gamma act on a space X, preserving a measure mu ergodic, and preserved by alpha. And we have a cocycle phi from gamma into GL VR. So is this setting of cocycles, and we want to make phi homologous to a cocycle which has some simple form, some simpler form. So in the case of amenable group, as I said, we saw how Zimmer theorems in this case give you that this phi can be made homologous to a guy taking values in an amenable group, and in particular in some sort of upper triangular picture modulo finiteness. Now here, different from the amenable reduction, the standard theory requires some L1 integrability, even though I think there are versions without the L1 integrability, but then they are harder to discuss. So it has to do with this fact that here I'm having GL and not SL. Okay, so this will have some input there. But let me put the statement in the strong form. So theorem Zimmer plus other people, because Zimmer gave the first version, then the version of each reasonable guy has a good version of it. So this is this way is probably given by Fisher and Margulis. But again, there are other versions as well of it. The very original is Zimmer theorem. So it says, assume for every gamma phi of gamma dot log of the norm of phi of gamma dot belongs to L1 mu. Actually, by the cocycle property, you only need to test it for a generating set of gammas, because by the properties of the norm of matrices plus the cocycle property, once you have for a generating set you will have for all of them. Okay, that's why it doesn't harm. Instead of talking about generators for gamma, I just ask it for every gamma. It's rather simple to test. Mu, yeah, probability. Mu is a probability. Very important. Good point. Which is a very non-trivial assumption, okay? Because these are not amenable groups, so you most likely will not have a measure invariant. Okay, then there exist two guys. There exists rho from.
Is it super important that you don't have invariant measure? Because I feel like I remember that for Zimmer it's always quasi-invariant measure, and like you have the Rodon-Nikodym derivative. And you have always quasi-invariant.
And here you really want the invariant measure.
Okay.
So the Rodon-Nikodym derivative will not be enough for the purposes. We will see the example. The example will be the boundary action, but we will see it. Okay. Okay, so then we have this representation, so a homomorphism. So G is SLNR, remember? And K from, so it's a cocycle, but is taking values in a compact group now, SO. So cocycle. Everything is almost everywhere here. Well, measurable. This also is measurable. Of course, I'm saying stuff about integrability, so better be measurable. So rho is better than just a cocycle because it's a cocycle which is constant. That's what makes a homomorphism. But it's not just from gamma, it's from G as well. Okay? So this includes a particular, so as a particular case of this Zimmer and Fisher-Margulis is what is called Margulis Super-Rigidity, which is when phi is independent of x, or let's say x is the one-point space, then you still have something like that. Still, there will be some compact game here, sort of cocycle. In this Margulis, let me just double check one thing. I don't want to mess up. At least I want to copy the statement the way it is. Yeah, that's how it's stated. Okay, yeah, there is. Yeah, I think it's essentially correct. Yeah, because I wrote this. Okay. So where were we? Okay, and let's write it. C from, oops, not gamma, x into GL dr measurable such that when I change my coordinates, I get rho of gamma times k of gamma x. And actually, this is a problem, and the problem will be solved in the next line, because this is a cocycle, this is a homomorphism, but the product of a homomorphism and a cocycle, or the product of two cocycles, will not be a cocycle in general, okay, because of problem with commutativity. If they were commuting, then it would be a cocycle, but they may not be commuting. And this is solved because rho of gamma times k gamma actually is eta x is equals to eta x times rho of gamma for every eta for every gamma for every x. So they do commute. So this compact guy, so the image of K belongs to a subgroup actually, which is commuting with the image of rho. Okay, so this can be actually reformulated in terms of image of K commuting with image of rho. Of course, if I want to write it down this correctly, I should talk about the essential image of K, because everything is almost everywhere here. But once I define the essential image of K, then I can take the closure of this essential image. This will be a compact subgroup here. And once I have this compact subgroup, the image of rho will be some other compact subgroup, and this translates into the fact that this compact subgroup and this compact subgroup commute one with each other. So every element in one commutes with the other. And that's it. So which means that then this product is actually a very nice cocycle, and not only is a very nice cocycle, more important than this is a very nice cocycle, is the fact that I have this representation that only depends on gamma, not on x. So it's a homomorphism which is fully classified by the theory of representations times a compact perturbation. Okay, so this guy will be growing. So you take any vector, you apply, and this guy can grow or not grow depending on several things, can be going to zero, whatever it does, and this will not affect this growth at all because it's compact. Okay, examples. So in some cases, you can get rid of this K. For example, it's not, I will talk about different type of examples in a second, but let's say D equals to N. Okay, so if D equals to N, then I have this rho from SLN to SLN. Okay, let's do the example here. D equals to N, then I have this rho from SLN to SLNR. Yeah, I should emphasize it's continuous homomorphism, so it's really a representation. And this rho is either trivial or an isomorphism. Okay, and this is just computing the kernel of this guy. So the kernel of rho is a normal subgroup of SLNR. SLNR does not have normal subgroup other than plus minus identity. So that's, you can forget about the minus identity without much of a problem here. And hence this guy is either fully trivial or an isomorphism. So once it is an isomorphism, you can just trick a little bit the action and the cocycle and assume it's the trivial isomorphism, so it's the identity map, which maps gamma to gamma or G to G. The other possibility is that rho is fully trivial, so sends everything to identity. So what does it mean then? That your cocycle is either conjugated to this rho. The compact should disappear because the only way you commute with all the elements in SLNR is that you are trivial. So this compact, well, it may be plus minus identity, but that's as much as it is. So if rho of G equals to G for every G, so actually let me write down the three cases. So the case I is this, case 2I is rho of G is G transpose inverse for every G, and 3I is rho of G equals to identity. So these are the three possible rows, and in this case I get, in case E and 2I, this implies that C of Gx phi of gamma x C of x is plus minus rho of gamma for every x for every gamma, and the plus minus depends on gamma and on x, but it's just a plus minus, so it's really nothing.
So here you're just using the simplicity of SL and R.
Yeah, to get this. To get this, well, I'm using a little bit more than just the simplicity. I'm using a very almost straightforward computation that allows you to know which are the continuous homomorphisms from SLNR to SLNR. It's not. It's just an exercise. It's in linear algebra. It's not very hard.
Well, simplicity of SLNR is also simple.
Yeah, but you need a little bit than simplicity. So just from simplicity, you get that this is an isomorphism or trivial. But once you know it is an isomorphism, why it is just in these two isomorphisms, you use it a little bit more. Still, it's not too hard. So in these two cases, so in any event, when it is an isomorphism, and for this you only use simplicity, I agree, you get that K has to be trivial. And in the third case, you get that rho is trivial, and so the phi is taking values in SO directly. And so it's by isometries. You're acting by isometries. Well, the cocycle is acting by isometries. Now, what is interesting is the following. Let me use, it is yet an example, but let me write it as a corollary. Is I could consider the determinant of phi of gamma x, call it d of gamma x. Okay, and just to forget about problems, I can take logarithm of the absolute value of determinant. And this is a cocycle. It's a real valued cocycle. And then the formula that appears there is telling me that d of gamma x is C is homologous to 0, is what is called homologous to constant. Okay, so even though the cocycle was taking values in GLD, it actually is taking values in SLD, essentially, due to this fact. And actually more, and same level of complexity as the previous one. It says that if D actually is a cocycle, then there exists C from x to R such that so there are no non-trivial R-valued cocycles. Okay, so that's what this thing is telling us. So the second follows from the first just by taking d equals to 1, and that's it, and a logarithm or an exponential. So if you have something like this, so proof of 2, if we take exp d goes from gamma times x into GL1R. That's it. And then you apply the theorem, take logarithm, and you are done. So this is the two most basic and baby examples. Now, one more important example. Yeah, maybe let me do a third example here, which is if d is strictly smaller than n, then rho has to be the identity, is by the same reasoning as before. So we have the simplicity, so then you get, so you're getting rho from, so this is either fully trivial or it's an isomorphism, but if d is smaller than n, there is no way you can fit. It's just a matter of counting dimensions. This has dimension n squared minus 1, this has dimension d squared minus 1, so there is no way. So, and hence this implies that phi of gamma x is equivalent to take values in SO. So it's automatically equivalent to compact. So it has to act trivially. In particular, you have I'm not saying that C is bounded here, but you will have, for instance, that lim of this is finite for every x, for every gamma, lim in n. Just to say something. Almost every x. And actually, you know more, okay? The whole point is, you know that this is C of x inverse k of gamma x, which is compact C of gamma x. Okay. So this lim is actually coming back to a Poincaré return set for the gamma. Now the next example is when we have gamma acting on Rpn minus 1, then it will not preserve a measure. So we saw it already, we used it actually, the fact that this cannot preserve a measure is the best manifestation of why gamma is not amenable. But we still have the derivative cocycle. We have d alpha x of gamma, and we can think of this as an element of GL n. Of course, for this I need to trivialize the bundle here, so I need to make some choices because this bundle it's non-trivial, remember that we have n at least 3 here. So this boundary is non-trivial. And we just make a choice of trivialization here. And then we have this cocycle, this derivative cocycle. Now, since it's taking values in n minus 1, so this is d, if anything like what we are doing before can be done, then the representation has to be trivial. So this should be conjugate to taking values in a compact guy. And it cannot take values in a compact guy, actually, because you take the derivative here and you can, well, we compute already the derivative of this guy for Cartan elements. And there is one eigenvalue which is not 1 if you are in the right position. So this in particular shows how important it is to take the invariant measure. Of course, one could try to modify the statements and find the true statement, and yeah, probably there is a true statement yet to be discovered. Okay, what is the correct statement for this? Probably, as you said, having to do with what is the determinant of this guy, which is the Jacobian. So that's probably will be an important ingredient for this if one wants to understand a general cocycle over a non-measure preserving guy. Okay, and part of the game we were playing in this course, which we never reached that far, but it should have appeared in the spirit, that when you have, which is in the spirit of the Margulis factor theorem, which is when you have a non-measure preserving system, then there is some boundary type of guy happening in some way or another. And so if you have a cocycle over a non-measure preserving system, then you may want to have some mixture between this very specific cocycle, which appears here, which is the derivative cocycle for this boundary representation, and then you have the other most standard cocycles, which are compact and independent of the point x. And maybe one can make some statement of the sort. Especially the question is, here is a question, if you want to work on it. Just a very, very explicit working question. So consider this gamma acting on Rpn minus 1. So the standard boundary action. So alpha gamma of L is gamma L. And let phi from gamma times Rpn minus 1 into R be a cocycle. Okay, so the simplest example would be log of determinant of the absolute value of determinant of this guy. Actually, it has positive determinants, or any multiple of this guy. So that there exists a constant C in R such that phi is homologous to C times log of determinant of the alpha. Okay, that these are the only cocycles, real valued cocycle for this action, no other one. Maybe false. If it is false, you find a counterexample. That's how we show something small. Here regularity, if you want to assume regularity, you can start assuming phi is infinity and still try to get this be measurable, where the transfer map here is just a measurable function defined almost everywhere with respect to Lebesgue. They are so here, since there is no invariant measure, if you want to work in the measurable category, it's reasonable to go and look at the measurable, at the quasi-invariant measure. And so, yeah, in this situation, I think it's reasonable to try with the quasi-invariant measure being Lebesgue, and and then do it for that. So we went through that. Okay, what else? How to prove this theorem? I just realized today that this is the last week of class. So yeah, we will not have time to prove this, but at least let me say a couple of words about the proof. So maybe a special case, as I said, is Margulis Super-Rigidity.
Margulis Super-Rigidity came before Zimmer Super-Rigidity.
Yeah, by far, yes. Way before. It came even before Margulis normal subgroup theorem, which still was way before Zimmer Cocycle Super-Rigidity. Yeah, no, Zimmer essentially got inspired and explored Margulis' proof, and he got his proof. That's why is Margulis a Fields medalist and not Zimmer. So, Margulis essentially says in our setting gamma a lattice in SLDR, in SLNR, and larger than 3, gamma into GL. Here, really, GL is not relevant. We have phi, a homomorphism. Here, you take the determinant of the guy. This will give you a homomorphism. You take the kernel of this determinant of phi, and it will be a normal subgroup. This guy has no normal subgroup, essentially. So you see clearly that there is no room for GL, it's just SL, but doesn't matter. Then there exists, let's still call it rho as before, from G, so this is our G into SLDR, and instead of doing the compact, you could do the compact, but here it's a little bit stronger. In general, you have to put a compact guy, but here I guess you can put this gamma prime. Can we? I think we can because it's SLR, but let me not do it. And phi hat from gamma into SODR such that image of rho commutes with image of phibar, and phi of gamma is of gamma times phi bar of gamma. Okay, so up to a compact factor, the representation extends to a representation of G, not just of gamma. It's pretty much what you get from there. And again, this is a homomorphism because these two guys commute. Actually, the fact that these two guys commute is a consequence of this being a homomorphism, if you want. So it's not really. Okay, so the proof of Zimmer is actually a reasonable, sophisticated, but natural generalization of this. So if you understand how to prove this statement, then it's not really hard to prove that statement. You just need to play a little bit more complicated action.
And in both of these theorems, rho is essentially unique, right?
Rho is unique, yeah, rho is unique. Yes. Rho is. So in this statement is really unique.
Yeah, here probably it's essentially
here, yeah, because you certainly have C, so you can conjugate rho by an element by inner automorphism, and yeah, there is no match, but yeah, you're right. So okay, I can do it. So how you get rho? Okay, we have a map just from gamma, but we really want a map from rho. Now, how you do it? You do it in the following way. So we again play similar to this normal subgroup theorem type of game, and you induce an action and then try to understand this action. Okay, so what is the action we are inducing here? So we have gamma is inside G, which is SLNR. Good. Now we have naturally gamma acting on Rpn-1, as always. So this is this boundary action we discussed some time ago. Now we are going to induce a gamma action on, let me just for simplicity do it here now, on Rpd-1. Now this is a very natural action by a lattice on Rpn-1. Now gamma is a lattice in SLNR, not in SLDR. But this I can induce with a phi. So how do I act? Alpha phi of gamma applied to L is phi of gamma times L. And phi of gamma is a matrix in GLD, so this is very well defined. So phi of gamma is not a lattice, is a subgroup, but is not a lattice, maybe a lattice. It's in general not a lattice in SLD. Okay, so it is what it is. But gamma still acts there through the image of phi. Now I have gamma acting here and gamma acting here. And if I can show in some way that this RPN minus 1 here sits in RPD minus 1 in an invariant way, so that the gamma action here is the same as the restriction of the gamma action here, then that's what the rho is doing, actually. Okay? Because if I knew rho was there, then what I would do is take rho of RPN minus 1, which is actually, to be more precise, this is rho of G mod P, and now this makes a lot of sense because rho will map G inside SLDR and will map P inside the P, because if rho is representation, it has to send P inside some P for the other guy. And so this will be inside H mod a PH. Okay, maybe P is not a good name because P is the maximal. So now this will be better. So this G mod Q, which is RPN minus 1, will be mapped into H mod QH. And then I have this guy sitting inside here. And I have this map rho from here to here will be gamma equivariant. And this is my conjugancy. And rho is smooth, say. Comes from algebraic origin. Okay, so what I'm looking for, so we are.
Shouldn't Q actually be P?
No, P is the largest dimensional boundary. RPN minus 1 is the smallest dimension. So this is the Q for the RPN minus 1. This notation is this is a matrix, square matrix. I'm putting all zeros here. I'm allowing anything else here. The P is.
It's a full flag.
This is P, where you have all zeros here, ones, not ones here, whatever you want. But in any event, so it is important actually to, we can argue with RPN minus 1, but if you give some room here, allowing some other Qs, it's even better. In any event here, we may not have the smallest dimensional guy. We may have just something smaller. But it's a good start. So what we are looking for by now is, let me change notations, little h from G mod Q into, just, now I'm just putting the piece for the time being, where I have gamma here, I have the induced gamma action here as well, and I want H measurable and the conjugancy. So that's the first step. So we are not getting as beautiful as rho would induce, because rho is a homomorphism, is a smooth map from the Lie point, so from this smooth geometry point of view. So this will be a C infinity homomorphism. If the H is induced by the rho, then this will be a C infinity map. Okay, here I'm just looking for a measurable map. So the first question is where to get this measurable map from. Once you get this measurable map, the second step is to prove that this H is smooth. How you prove this H is smooth is by some sort of measure rigidity, the way we have been doing so far. Now, the last step is once you know that this H has good enough smoothness, how to build the row. Okay? Building the row is not hard. What is hard is proving that the row you built is what it has to be. Okay? So let me tell you in 2 seconds how you build the H first. Let's go up there. And maybe let me just add the fact that when you want to do Zimmer, you essentially add here a times x. And then in the x variable, you just want everything measurable, and you will work in the other variable. That's really how you adapt this to do Zimmer. So how to build H? Well, we have gamma acting, well, not just acting, but, well, it's, well, you have this phi map from gamma into H is GLDR. Okay, so this means that if I, for instance, look at G mod gamma, I can define a cocycle of gamma times G mod gamma. It's a measurable cocycle by just, in a sense, using the integer part function. Okay, so phi of gamma G times gamma would be, I have to take a representative, and this, I think, how I'm supposed to define it, I think it's essentially gamma. But I have to do something here. I wrote it, but now I forgot, so yeah, let me not write it now. But essentially, you induce from here this cocycle. Maybe next Wednesday I write it more explicit. You do the coherent way, and it just is doing. But now this guy preserves Lebesgue measure. I have this gamma action. Okay, so I can do actually the whole G action. Yeah, I'm sorry. I define even a G cocycle here now because if not it was obviously trivial. Yeah, that's how you define the obvious way. So a G cocycle for this G action on G mod gamma. And once I have this, I can restrict this phi gamma to A. A is diagonal matrices. And now I apply Oseledet's theorem to this phi hat guy. Okay? Oseledet's theorem will give me a flag. So I get a flag phi sub dot from G mod gamma into the corresponding flag space. This flag is A invariant. I can lift this flag into here, just G mod gamma is a quotient of G. So this flag will be A invariant and will be P invariant as well. This requires a proof, but it just follows from Ocellet's theorem and the basic property for the flag. So if you look at the corresponding invariant subbundles, they are not invariant, but the flag, it is as a flag invariant by P. Okay, that's why you already work with the flag. So it's like the forward oscillates. You don't do the bilateral oscillates. You only do the forward oscillates. So this is P invariant, which means I have this G mod P. And this is flags in RD. Flags in this RD will be equal to GL dr quotient sum Q sub H, where this Q sub H corresponds to whatever dimensions I'm getting from this flag. That's it. That's how I get H. Okay, I think I really consume all my time. So yeah, more than my time. So what I will do, hopefully on Wednesday, is I will take 5 minutes and write down explicitly. So I want really you to see how straightforward is this, and also explain probably a little bit better how is these flags coming from ocellates and why you have the P invariant, because this is really very, very similar as what we did for the probability measures in the proof of normal subgroup theorem. So I want really to make sure it's clear for you that this scheme is not so different from what we did with normal subgroup theorem.
And so here, P sub H, by writing P sub H, you mean Q sub H. And it doesn't.
Yeah, well, it's Q sub H, I agree, but yes, Q sub H, yes, you, yeah, because the P sub H actually goes down there, so you may not be able to lift it. Yeah, you're right. So this is a Q sub H. So it's some Q. Actually, I could do, and typically that's what Zimmer does. So this will fiber naturally over the maximal one, so RPD minus 1. So down there, here there is no problem to put in RPD minus 1. Then this P here will be whatever it is. So it is the maximal P, but you then look at the optimal guy where this F is constant. This will be a Q. And then you will have the Q here. And this may be not be RPN minus 1. It will be just some G mod Q. Doesn't matter. So you just need to get this. So that's how essentially Margulis did the first step. So it is pretty much how he started. So with Ocellet's theorem. Okay, that's it. On Wednesday we see how to follow. See you on Wednesday. So it's a very standard construction, but it's very important as well. And it's essentially a triviality, but it's very useful in terms of this inducing that we were using a lot in these lectures. So let me just do the easy statement, or well, I can do. Okay, let me do the easy statement, and then we go to the general statement. So remember what did we have? So we have this homomorphism here, and we wanted to induce a cocycle for the G mod gamma action. Okay, a G cocycle. So of course, what we want at the end of the day is to have an extension of this rho to the homomorphism of G. But since we are not being able to do it right away, so the first thing is to try to extend it to a cocycle. over this G mod gamma action. Okay, some rho hat, which would be a cocycle. Now, actually, what we are going to do is something a little bit more universal in a sense. So we will define a map gamma hat from G into G mod gamma into, gamma, which will be a cocycle. And once we define this gamma hat cocycle, then we apply rho to this gamma hat, and this will be a cocycle as well. Okay? So now the question is how to define this. And the way to define this is the most natural way possible, essentially. But what does it mean to be the most natural way? So the point is that in this writing, it will depend on some choices, this gamma hat. So it's not, even though it has some universality in a sense, it depends on some choices. So we fix sigma a subset of G, a fundamental domain. For G mod gamma, so that when I do sigma times gamma, we get exactly G. And so that sigma gamma intersection sigma is empty for gamma different from identity. Now, once I have this, I take any G. Well, first of all, I take any element of the form x gamma, and I take any element G, and the natural element associated will be Gx times gamma. That's certainly the natural element associated to two pairs here. But now I want to keep in mind what these G are doing and what these X gamma are doing. So this Gx gamma will belong to some fundamental domain times, well, forget about the gamma. So this guy will belong to a fundamental domain some, not gamma hat, let's call it gamma bar of Gx. Now, on the other hand, X will belong to this guy. Now, this is not fully so both X and Gx are not fully well established because my knowledge is about X gamma. So the natural choice here will be to pick X in the fundamental domain, in which case this gamma bar will be just identity. And then this will be a guy which is uniquely determined. Now, if instead of, for some reason, I'm taking an X which is not in the fundamental domain, still things should be good because I will have here the X belonging to this translate of the fundamental domain, and then the Gx will be essentially the corresponding translate. So let me write down what I'm saying here. Let me just make a slight writing. Okay, so let me define then very explicitly the two guys we are talking about here. So one is this gamma bar, which goes from G into gamma, where gamma bar of X is such that x belongs to sigma times gamma bar of x, or equivalently x times sigma bar of x inverse belongs to sigma. So this is the definition of gamma bar. Then there is associated a function sigma, which goes from G into sigma, which is pretty much this function here. But which is also the same as x times gamma intersection with sigma. Okay? So that's also an equivalent definition of this sigma x. Okay, so once I have this, just make sure. Okay, then I define this gamma hat. So define gamma hat of G x sigma as being this gamma bar just defined apply to G of sigma of x gamma. Okay, so what I'm doing is I'm taking this G, and in a sense I'm taking the integer part of this G. But I have to be careful, because if G were over the identity, that's what I'm doing. But if I'm, instead of taking the identity here, I'm taking an x which is close to a boundary, then when we apply G, I most likely will jump to a different fundamental domain than the identity is jumping. And so I want it to be a different gamma. So this integer part should be different. And that's why this, I'm not defining this as being just gamma bar of G. I'm doing this gamma bar of this sigma x gamma. Okay? So okay. So this is this gamma hat, and the basic claim is this gamma hat is a cocycle. So i.e. gamma hat of G1, G2, x gamma is the same as gamma hat of G2, G1 of x gamma times, no, this should be after, so this is gamma hat of G1, G2 of x gamma times gamma hat of G2 gamma. Okay, so I think that's the cocycle property, and let's check it if it is true. Okay, so have to show what's the value of gamma bar of, so proof of lemma, of G1, G2 sigma of x gamma I need to know what is this value, but I will compare it versus the second line, which is gamma bar of G1, G2, sigma of G2x gamma. Oops, no G2 here. Now I think it's correct. Times gamma bar of G2 sigma of x gamma. Okay, so that's the two guys I have to compare. Now, here is an important property of the gamma hat, of the gamma bar. So gamma bar of x times eta is gamma bar of x times eta. So the integer part has this translation invariant property, just by definition. So I can bring this gamma bar inside. So this guy here is the same as gamma bar of G1 times sigma G2 x gamma times gamma bar of G2 sigma x gamma. Because this is an element in gamma, an element in gamma gets inside. Well, but the good news is that sigma y times gamma bar of y is y. So this guy is the same, so these two guys get together, even though there is a sigma of x gamma that I'm missing here. That's bad.
Well, but you can open sigma up.
Yes, very good point. Exactly. So second property is sigma. I can open sigma up. I want to open sigma up, or
You can lift
yeah, I guess I should open sigma up. Let me just double check that whatever I'm writing is correct. G1 times sigma of G2 x gamma. That's very good. This is gamma bar of G2 of sigma x gamma. That's right. So this is correct. Now I should open it up. Still, it's strange because if I had a sigma here, then I will be right. This will be correct. So this is the same as the guy downstairs where the sigma is there. Which means that that's what I am supposed to get.
somehow you're creating double sigmas.
Yes. It's not that bad after all, but I'm really puzzled about this. So, well, let's open it up, okay? What to do? So remember the definition of sigma x is x gamma intersected sigma. So sigma of G2 x gamma, well, sigma of x gamma to be more precise, this is the same as G2x gamma inter sigma.
So is sigma defined in the quotient or the?
Yeah, it's defined from the quotient. Oh, okay. Yeah, I defined there, but actually I really care about the quotient. You can actually look at this as defined from G, but it's gamma invariant, so it's really a function from the quotient. Yeah, there is something I'm not liking here. Let me see my notes. What is wrong here? Let me see if I define it correctly. G of sigma x gamma. Okay. Okay. Very good. Very, 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 very good. Very good. Sigma of G2 x gamma. This is the same as this. And this I claim so we have this. Just wait. Yes, and this is, and the claim is that this is the same as doing G2 sigma of x gamma times some guy that we shall call gamma 2. Okay, so it's a translate of this G2 of sigma x gamma. Okay, so that's the claim, and the proof of this claim is just the fact that these two guys belong to the same gamma orbit. So as soon as sigma G2 x gamma belongs to the same orbit of G2 sigma x gamma, so that they are the same lift of the guy downstairs, then the difference is some gamma 2. Okay? And actually this gamma 2 should be quite explicit. This gamma 2 is gamma bar of G2 x gamma. Gamma hat, I'm sorry.
Cancel out. Thank you. Because you're getting everything that you need, except that you have gamma 2 times gamma bar of G2 of sigma x gamma. So I would guess that gamma 2 is the inverse of this residue term.
Maybe you're right. Let me see. Okay. Let me start over. Okay, let me follow my notes instead of trying to guess. So, claim 1, call gamma 2 equals to this guy there, gamma hat of G2 x gamma, and then sigma of G2 x gamma is G2 x sigma of x gamma times gamma 2. So that's the first claim. Then claim 2. Claim 2 is actually the proof once we have claim 1. Let me double check. Claim 1 is correct. No, claim 1 is not correct. This is sigma of this times gamma 2 is equal to this. Now is correct. And then claim 2 starts computing. So when I do this, actually, let me be explicit. G2x gamma. This is gamma hat of G1 gamma 2x gamma times gamma 2. And eventually I should reach the gamma hat of G1 times G2. Okay? So this is the same as gamma bar of G1 sigma of this. This is gamma 2, this is G2. G2 x gamma times gamma 2, which, since it is a gamma bar, I can put it outside or inside. Doesn't matter, so I'm putting it inside. And then I'm writing explicitly, well, this being equals to this, and I run into the same problem. I made a mistake. I wonder where is the mistake. Now I really mess up.
Like, gamma 2 is exactly this rigidity.
Yeah, but then I'm really running into some problem here. Maybe
You can unroll this thing. Oh wait.
Times, and then I have definition. This is gamma. Well, actually, I can use this formula. Oh, okay. Yeah, no, yeah, you're right. My bad. Yes, you use now this formula, and this is just G2 sigma x gamma. Okay. Yeah, my bad. I was trying to do some extra constraint computation. And yeah, this is, by definition, gamma hat of G1, G2, x gamma. And then we are done. So modulo claim 1. Now we need to check claim 1. So proof of claim 1. Oh, I thought I was completely wrong. Now claim 1 again should follow directly from definitions of sigma. So what do we have in the left hand side? In the left hand side we have G2x gamma intersection sigma times gamma 2. And in the right hand side we have G2 times x gamma intersection sigma. Okay? now they are the same. Now, why are they the same? So the reason why they are the same is the following. So this guy here, in the left-hand side, the guy in the right-hand side. Yes. This guy belongs okay, this guy is the same as G2x gamma intersection G2 sigma. Okay? Now, what is gamma 2? Okay, gamma 2 is this gamma bar of G2x sigma, which means by definition that G2x sigma, that G2x is in sigma gamma 2. So this guy also belongs into here. Okay? Now, this guy here is a subset of this guy here. So this point is determined not just by this double intersection, it's also defined by this triple intersection, because it's just always a point, and it's contained in this intersection, which is a point, or this translative intersection, which is a point. And so they have to coincide. So a point equals to a point. I'm sorry, but yeah. Honestly, I cannot tell you how one is supposed to come in their mind with this computation, but I guess I once came in my mind with this computation, so in some way it should be somewhat natural. Okay, so I guess if you play enough, it becomes very natural thing to do. But well, this gives you the claim 1, claim 2, you get that this is a cocycle. I think there is probably a better way of explaining this cocycle, and with a better way of explaining this cocycle, it should be even more natural that it is a cocycle. So if you want, the natural way why this is a cocycle is because you can do, so you have the gamma action on G mod gamma, and you have the suspension of this gamma action on G mod gamma, and this suspension of the gamma action on G mod gamma is essentially a G action which will be corresponding to this cocycle here. If you take the natural trivialization of G of the suspension coming from this sigma. But anyway, let's not continue stuck on the same place. So this is a cocycle. Then we can define this rho hat cocycle now into SLDR, which is rho hat of G x gamma is rho of this gamma hat of G x gamma. And since rho is a homomorphism, this becomes automatically a cocycle.
I mean, can't we just think of gamma as some sort of a deck transformation group of
Yeah, gamma is a deck transformation group, and yes, you are just telling you what is the deck you are when you apply the G. Yeah. Okay, so this is a cocycle. G lambda preserve, so the G action on G lambda preserve lambda, the Haar measure, and so we have this G action on G mod gamma preserving lambda, and this is a cocycle for this G action. Okay, now we are not going to apply Zimmer Cocycle Super-Rigidity here because we are going to prove Margulis Super-Rigidity, so this before. We neither are supposed to apply Zimmer amenable reduction because this also comes after Margulis, but Ocellet's theorem comes before Margulis. So we can apply Ocellet's theorem. Okay? And so we take a subset, so the Cartan subgroup in G. So remember, for us, G is SLNR. And we make a choice, because to define really Ocellet's and all this stuff, I need to make a choice. And the choice is this A plus, which are all these e to the lambda 1, e to the lambda n, such that lambda 1 is larger than lambda n, all not positive. I'm sorry, because the lambda is, no, yeah, the sum of the lambda i's are 0. This choice of Weil chamber for this guy, and then Ocellet's theorem will give me a flag, but I can actually be a little bit more explicit with this flag essentially. So I can make the choice of the basis for this Ocellet's theorem, and there is something here to be discussed a little bit more carefully, but still let me not make it. So you give me a function C from G mod gamma into SLDR such that, so measurable, such that when I do the composition and I take rho hat on G x gamma, this change of variable, now it's be a matrix in SLDR, but it preserves a flag. So which means that this belongs to a group, some group, which I call it Q sub H, which is a group which has a lot of zeros below the diagonal. This essentially should be the P, but there may be multiple Lyapunov exponents, and then it may have a little bit larger Lyapunov exponents, multiplicity of the Lyapunov exponents, so you may have two guys that you cannot split. And so that's why it's actually QH and not just one guy. Of course, why this QH is not all SLDR, this requires some explanation. Let me not do it. Okay. So to A plus.
And so they all have to be one-dimensional.
No. No. Here is an example. take d equals to 2 times n. Okay, and then rho is actually a rho of g is this. Then I get e to the lambda 1, e to the lambda 1. So for the SLN action on SLN, yes, you have this. Actually, Margulis get rid of this problem very quickly, asking for, so you first do some reduction, asking for some irreducibility of the guy, and then, so yes, actually, to be honest with Margulis, he knew, I think by that time he already knew, and I'm not sure whether he used it or not, but he certainly knew that, yeah, these are into one-dimensionals. So it's what is called simplicity of the spectrum. But I don't think you need it, okay? So you do need essentially to show that this QH is non-trivial. Yes, that you will need. So meaning not everything. And actually, when you go to Margulis, he does it for any group G and for any other guy here. So you may land in a bad situation where actually you cannot prove that this group is trivial, not all SLD. So SLD is really not giving you much of the decomposition. So all eigenvalues are the same, all the Lyapunov exponents are the same. But then he proved that this belongs to SO, to a compact group. And actually, that's how Margulis Super-Rigidity goes through. So actually, either rho, I think I wrote it in this way, I'm not sure, that either rho comes from a representation or from a compact guy. And indeed, in the more general situation, is the product of a representation of the group times a compact valued homomorphism. So, and all this information happens already from oscillators. Okay. So, modulo then all the discussions here, you get this, where this is a non-trivial parabolic group. And when I have this guy, I can think of this map, Cx. Let me see if I'm doing it correctly, as an element of SL dr mod QH. I'm not sure whether I should quotient to the left or to the right. Okay, let's do it slowly here. So what I want actually to do now is first of all extend the C to a function from G into SLDR. And the claim is, and this claim follows from oscillates, so it's consequence of oscillates, is that if I do rho hat of Px gamma, on this, wait a second, what I'm doing here. No, that's not what I want. I want to do this function, this is C, is the function. Okay, let me write it down and then I correct it. So this induce a function from P mod G into SLDR mod QH. Okay? It's either C or the inverse of C who is doing this job. And this function will be equivariant when I apply gamma here and I apply the induced action of gamma in here. So what is the induced action here first is, let's call it alpha, this guy. So alpha gamma applied to A, use it A already, so to X is rho hat of, well, it's not rho hat, it's just rho gamma of X why I'm having so many troubles here. Okay, let me define this better. Okay. Let me do this a little bit better. So on P mod G times SLDR mod QH, I define a G action here, which I call alpha, which take alpha given an element G and an element P times H and Q times X. This gives me as an outcome PHG, and in the second coordinate I do QHX, and then I do rho hat of X, not of Rex, but of G, and then first coordinate is H. H times gamma, I guess. Something like that. So yeah, just to make first instance, let's do it just like that. Let's forget about this and let's act into this product this way. Now this is perfectly good. That's how you act in the product of these two groups. And the graph of G is going to do something very important here. Okay? And exactly, the graph of G here is P times QH equivariant with respect to this action of alpha. That's what will be the right property. This.
I mean, it's believable.
Hmm?
It's believable, but
Okay, yeah. I'm really messing up a lot here. Yes, and I guess we are almost on time. Yeah. Let me just, in any event, try to explain. So my point is that I wanted to write a proof of this Margulis Super-Rigidity using what we wrote in the proof in this course, and I'm still in the middle of the writing, so I didn't finish it yet. So I'm trying to fix it, but certainly I'm not being able to fix it now on the blackboard.
So essentially you're trying to switch the right gamma quotients on both the coordinates to left parabolic quotients.
Yes, something that we already did in this normal subgroup theorem, and I'm trying to do it again. So what I'm writing in my notes suggest is that I consider this G action on the product space, which is a skew product action. That's always when you have a cocycle, you can always define your skew product action without problem. And actually, I could quotient here by whatever other subgroup, because this will naturally go down. So the point is to consider this action and then use this C to define this measure, which will be P invariant gamma equivariant. So similar to what we did for the normal subgroup theorem. So I need to get this measure. So this P invariant measure on this space. Of course, this space is very non-compact because of this SLDR, but the whole point is that once this guy, the error of this guy comes into QH, if I quotient by QH, then this C is not making any mistakes because I quotient the mistake. And so I actually get an equality there. So on.
So you need to change the second coordinate of alpha using the C.
Exactly. So I'm just claiming the following fact. If I do rho hat of, yes, that's exactly what, so it's still a quotient to the right, not to the left. Probably that's why I got so confused for a while. So when I take this guy times C of x gamma, and I multiply this guy by QH, I get that this is the same as CGX gamma times QH. So this formula is exactly the same as this formula. Which means that when I quotient by QH, so when I look at this as a function from G mod gamma into SLDR mod QH, this formula is telling me that the graph of this function C is an invariant set in here for the G action here. So I'm getting a measure on this G mod gamma times so I'm getting this graph of C inside here, and as before, this graph is actually a nice set that projects to Lebesgue here and is an atom on the fiber. So I can regard this as a measure. Now I should leave this measure as before, as we did with the normal subgroup theorem, to this space G times this, and regard this measure, so prove a p-invariance property of this measure. This is some p property of the C, and it's just the fact, well, let me go back, wait, let me go back a little bit here. So first of all, this is only true for A in the Cartan. Now you prove, working a little bit hard, but not too hard, that this is also true for A in the P. And that's all you can show, that this is just true for guys in the P. So this graph, first of all, is only P invariant, it's not fully G invariant. Okay, still anyway, so it is G invariant will be gamma nicely. So we do as before, we lift and use the P invariance to show that when you look at some gamma action, some induced gamma action here, this measure is gamma equivariance P invariant. So you get a measure there. Okay. Once you reach this level, you are essentially in pretty much the same sort of a scheme like in Margulis factor theorem, and you actually go to the suspension again, because that's how the proof of Margulis factor theorem goes, is going to the suspension and considering again the P and the A action here. But the end of the game is that this graph that we are having here, which is in principle a graph of a measurable function, you show that is the graph of a smooth function. That's the key of the game here. So you take the eigendirection, so you go back to Ocellets' theorem. Now is the bilateral Ocellets' theorem, which will correspond to an Ocellets in the base, Ocellets in the fiber. Here, the Ocellets in the base, you understand, because it comes from G. The Ocellets in the fiber is just Ocellets, but you show that with respect to this Ocellet here and there, the measure, so you have one direction here, so it's a product space, and the measure is actually a line. No, it's actually a line. So it's a homomorphism from this direction here on the base, which is this root direction, to a direction in the fiber, which will be at the end of the day some sort of root direction. And this linear map, it's defined from this root space to this root space. And this graph essentially is what will become the rho at the end of the day. Now, I don't know how to do the end game by myself. I know how to come back to Margulis proof, essentially. And in Margulis proof, what you do, and let me finish even though I'm over time, with the comment on Margulis proof. So you just go back all the way down to the beginning, and you look at rho, to the graph of rho, as a subset of G times SLDR. Okay, it's actually inside gamma times SLDR, so, but this is inside G times SLDR. And now you do what you do in a lot of theorems in analysis. You take this graph of rho and you take the closure. If this closure is nice enough, this closure will project into the first coordinate into all of G. And actually, the projection in the second coordinate will be just 1 to 1, meaning that this graph, this closure of the graph is still a graph. And then if this closure of the graph is still a graph, then you are done, because it's a graph of someone. And that's so once you are the graph of someone, then it's a very easy exercise that if this graph of someone is a group, then this someone is a homomorphism. Now, the only thing you use there is that this graph there, the closure of a group is a group. So there are two things here to understood is one, the closure of a graph is a graph. So why don't you have in this closure two guys over the same element? So then I cannot define. Well, and second, what does it mean to take the closure of a discrete set and getting not a discrete set? Okay, not the same set. So this graph is inside this gamma, and this gamma is discrete. So where does accumulation comes, and this is this notion of Zariski density here, where it is actually a very rough topology that closure of sets is huge. So gamma is not anymore discrete with respect to this Zariski topology. So this closure is really something important. So that's one thing. And essentially, what is this closure is you take the smallest polynomial that vanishes on gamma, and that's it. So it's this zero set of this polynomial. Now, of course, this most likely, since it is so rough, most likely you would expect that the closure of this graph is actually the whole G times SLDR. Okay, and then there is no way this is a graph. So the whole proof comes into showing that this closure is something. Now, what is the good news? Is that you already work a lot, and you knew that the guy is a graph on these subspaces. And then, if this guy were large, like all G times SLDR, then this measurable graph that appeared here will essentially contain this graph, and so it cannot be this business here. Okay, so that's pretty much the idea, and the reason for that is that this line here is algebraic, this line here is algebraic, and this line here then is algebraic. So the Zariski closure is telling you that, well, the Zariski closure of the gamma here is the same as the intersection of this closure with this two-dimensional space. So it has to be a line, cannot be in two-dimensional. So that's roughly what is the proof of this Margulis Super-Rigidity that goes through this Zariski closure. I think that there is a way of not going through this Zariski closure, and I think philosophically that this taking the measure is the nice geometric counterpart to taking Zariski closures. So all this process that we were building here of measures is really should be taking already this Zariski closure into account. But well, anyway, and it's already more than 10 minutes, so sorry. I still will come back on Friday and talk about some slightly different, but still same sort of cocycle rigidity statements. Okay, and that will be all. Thank you. Today, the idea is to do a slightly different type of cocycle rigidity statement. So it's the last day of class, so I certainly will not cover everything, but I want to discuss it a little bit. Okay, so let me show a different type of cocycle. So remember, we gave a definition of cocycle, which was there was an action, and you had some sort of group property where you take the product of these two elements and you want it to be something like this, say G1 at G2x times phi of G2x, something like that. So a chain rule type of formula. Okay, so this is what are called untwisted cocycles. I will introduce some guys which are called twisted, which means that the group will be abelian here. So no, one can do Schmorzian groups, even though it gets complicated when the groups are not abelian. But still, let me do it now. So what is the setting? So the functions phi we are looking for will be from the group acting times the space where the group is acting into some space. B comes from Banach because for the application will be a Banach space, but what is important of this Banach space is that it's an abelian group. So you're thinking this Banach space is an abelian group. And then you have a representation, I want to call it beta. Check my notations, yeah, beta from the group, and I'm sorry, but let me call the group gamma because I will be using G as well. So into bounded linear, so let me just put like this, homomorphisms of B. So that's a homomorphism so it's just a representation of gamma into this space B. Okay, in general, just by bounded linear operators. If this is a Banach space, I want the image, so beta of gamma, to be a bounded linear operator. But for the definition of what I'm willing to say, that's good enough. And now I want some property for this phi, which is the cocycle property. Okay, so what is the cocycle property? Will be that something like above. Now is an additive property, so if it just were going to be a cocycle, this would be, oh boy, I hate when I write it in such generality that I don't even understand what's going on. Okay, then this will be rho actually, not beta. That's not so serious. Okay, so this would be phi of G2x. And then here we would have phi of G1 in G2x. Okay, so this would be a cocycle. But now comes the twisting of the coefficients, so it comes this rho. So here we will have a rho of G2. Let me see if that's G2, that's G2, yes, good. Exactly, very good. Actually, for whatever purposes, I think I may want to put an inverse here, but that's, again, that has to do with left versus right actions, so it's not so serious. Okay, so because when I do G2, G1, if I want this to be good, I need to bring the guys out, so probably we want an inverse here, so that this is a good notion. So this is a cocycle, a twisted cocycle. Cocycle twisted by beta, by rho, I'm sorry. Okay, now all these names, cocycle, coboundary, cohomology, come from an actual true cohomology business here. So, which is the cohomology of the group gamma here, which is the acting. You can go and define the HK cohomology of gamma acting on this B. We are only going to do the H1. Okay, so let me do it now and I will try to convince you that I'm talking pretty much of the same definition. So yeah, this will not be the same Banach space, so let's call it B1, this guy. This is one group. The one that will appear here is a second group. So we are going to be given beta from gamma into these homomorphisms, actually isomorphism, but anyway, of this B1, not B1, now it's B. It's another guy. So it's a representation. Which typically, when for people doing cohomology, what you are taking is this is a module, but is not just a module, it's a gamma module, what is called a gamma module, and this gamma module is being a gamma module via this beta. Okay, so
I guess you're doing discrete type cohomology with operators.
no, but it's so far it's just abstract cohomology theory. So anyway, so that's what it is. So you have this embedding of gamma into the homomorphisms of P, actually into the isomorphism, because it's an embedding and gamma is a group. This will be isomorphism. And then we are looking to this guy, which I denoted this way. I put the beta here, even though people don't put the beta there, because B inside B is already understood beta for the people doing cohomology, but I'm not a cohomology theory guy, so I need to see the beta somewhere to know what I'm talking about. And this is, as any first cohomology group, is kernel divided by image. Now the question is kernel of whom and image of whom. So it's kernel of some D operator divided by the image of another D operator. Now, what is the kernel? The kernel is the cocycles. So here are what are the cocycles. Let me make sure I'm not messing up. So the cocycle will be a formula pretty much the same as this. So phi belongs to ker. Here means phi goes from gamma into this B. Okay, notice that there is no x here. It's just this. And satisfies some sort of formula, which is, if beta were trivial, it would mean that it's a homomorphism. But beta is not trivial. So it means that for G1, G2 is I hit with G2 by this beta phi of G1 plus phi of G2. Okay, so and you see that if beta were trivial, then this would be exactly a homomorphism from gamma to B, but beta is there, so this is a non-trivial type of homomorphism.
This is just group cohomology.
That's just group cohomology. That's just exactly standard group cohomology. Now that's kernel. Now what is image? Well, the D operator is the following. Take U in B such that phi of gamma is u minus beta of gamma u followed by gamma. So this is the d operator. That's d of u. And this difference is d of phi. Okay, so here du is at gamma is u minus beta gamma u. And here d phi at g1, g2 is this difference. So it's phi g1, g2 minus beta g2 phi g1 minus g1, g2. And so it's
0 here recovers the fixed points.
exactly. Exactly. So, which is that's a very good observation, because what is H0? H0 is supposed to be the connected components from topological point of view. Okay? Now, as you said, from this algebraic perspective, H0 corresponds to the kernel of this, du, which corresponds beta gamma of u equals to u. Okay? So corresponding to the invariant vectors for this representation. Okay? Now, if you remember, invariant vectors correspond to ergodic components. Because ergodicity means the only invariant vectors are the constant ones. Lack of ergodicity is the fact that you have invariant vectors which are not constant. And when you do the ergodic decomposition, what you are identifying is all these invariant vectors. Now, ergodicity and connectedness should be regarded as the same type of notion. So one is in topology, the other is in dynamics or in ergodic theory, but this notion of indecomposability. Now, again, this beta here is just a representation. So to talk about the ergodic theory, we should go back to some action. And now let me tell you how the cocycle upstairs is actually the same as this cocycle downstairs. So actually we define B as being the space of functions psi from x into B1, and then our representation beta from gamma into B will be beta gamma of a function phi. Phi is an element there. Wait a second, because why I want. I guess. Yes, but I hope I'm not forgetting. No, okay, good. So this is exactly. So that's exactly. Yes, you do rho gamma inverse phi of alpha of gamma, or just gamma x, because we use this notation. So this. So your beta is, that's why I need the gamma inverse over there. Okay. That's the right action. Yeah. Okay. So I compose here with gamma, and then I hit by this action on B1, which is by rho. And then you see that the cocycle property upstairs and the cocycle property downstairs are exactly the same cocycle property. So having a function, yeah, maybe I should put psi here, not phi. That was confused me. I put there, but then now if I take a function from gamma into B, here, this is now a function phi from gamma into B, what means is a function phi that to each gamma I apply to an x and it's an element of B1. So this is the same actually to considering a function. So considering a function from gamma to B is the same as considering a function from gamma times x to B1. And once you make these identifications of from gamma to B to from gamma times x to B1, these two notions of cocycles are the same. Actually, here above, I didn't say what was the meaning of being homologous to 0, but it's exactly, now that we know, it's exactly whatever is down there. Okay, let me do one more even more explicit example, okay, which really put us very close to what we were discussing during this last week. So we have now again an action from here. An action from gamma into space X. Let me do things correctly. Yes. Now let's just take this B1 as being Rn, or Rd actually, better than Rn. Gamma is a lattice in S and R, pretty much as we were working. And indeed taking n equals to d makes it not even simpler, it just gives a more concrete example, but I don't need to go to a more concrete example. Now I'm given rho from gamma into SLDR. Okay, and this d is the same as this d. So I have naturally, so this is what I was calling homomorphisms of Rd. These are the invertibles. And actually, if you want, you can make them GL valued. We know it has to be SL valued because as soon as n is at least 3, we know what's going on here. But now, really, this is pretty much the same. These are the invertible homomorphism. And now I take this function phi from gamma times x into Rd. And let's imagine this is a cocycle. Then I will define a function phi hat from gamma into GL d plus 1 R, adding a column. So what is this guy? I need to be careful. But here is pretty much what the guy is. I take this square here, this d times d square, and I put rho of g there. Maybe rho of g inverse. No, I think rho of g is correct. No, maybe rho of g inverse. Yeah, maybe rho of g inverse. And then in this column here, I put phi. And then zeros and then 1. Now the cocycle property for phi translates into cocycle property for phi hat. So it means that I can apply Zimmer Cocycle Super-rigidity again. If I assume that this guy preserves a measure, so there is a measure here which is invariant by alpha and ergodic, then I can make this cocycle homologous to a constant coefficient cocycle. Okay? Moreover, you can check that this constant coefficient cocycle actually will be pretty much of the same style, so you will have the same Roshi here, and you will have just this guy here being 0. Okay, so essentially you can kill the phi, and the transfer function C of x will be a matrix which is identity 0, 1, and some function u of x here. Okay, and this function u of x is the one trivializing this cocycle here. So trivializing this guy and trivializing this guy is exactly the same, first of all. And second, we know by Zimmer Cocycle Super-rigidity plus some exercise that this cocycle is trivial, assuming n is at least 3. Measurably. So there is a measurable function trivializing this, assuming phi was measurable. Now what I want to discuss is a little bit more than that, is how to show, assuming some condition on rho and some condition on alpha, essentially almost no condition on alpha, but some condition on rho, that this action, this cocycle, and hence this cocycle is continuously homologous to trivial. So that this measurable function that trivializes the guy is actually continuous, not just measurable. So in other words, if we go back to this cohomology theory, if I now take this B guy, this capital B guy, which was supposed to be the space of functions on B1, instead of taking the measurable functions, I take continuous functions now, I'm showing that this is 0. That this H1 is trivial. Okay, but for this I need hypothesis on beta. Because as I said, I need a hypothesis on rho, so this requires hypothesis on beta. And let me state it now in purely cohomology terms. There is a lot of dynamics spacing theory coming behind what I'm going to state, but it's a purely cohomology statement. So let me try to write it down. Let's move it back there. So
I have one literature question. In the
yes.
Zimmer book,
Mm-hmm.
it finds the cocycle as a twisted cocycle to begin with. Is that true?
Could be yes. That's the most general. Then of course the twisting can be trivial. Yeah, that because actually that's when people do group cohomology, they assume that the coefficients are twisted. And again, it could be trivial twisting, so it's untwisted, but it's a natural framework. So let me write down the assumptions on beta. Okay, so we take B now a Banach space. And here gamma will be a lattice in SLNR. which is what we call G. So we are doing this case. A, as always, is the abelian, the maximal Cartan, the diagonal group. I don't think I need the K. And let me see. Yeah, that's B is the Banach space. So this is the Banach space. This is gamma. This is G. And then I will assume that there exists beta first from gamma into now bounded linear maps of B. And we will assume there exists a rho, which is pretty much the rho upstairs, but is more abstractly. So from G, not just from gamma, that's very important, into into bounded linear maps of B as well. Such that for every B in B, and for every G in G, and for every gamma in gamma, when I do rho of G times rho of gamma times beta of gamma times B, this is the same as doing rho. The norm is with respect to the Banach norm there. So what is this saying is that this operator here, okay, is fully neutralizing the beta, okay, which is pretty much what we had before, in a sense, because this beta gamma was rho of gamma inverse applied to phi composed with something. So I'm taking out this rho of gamma from the beta and forget about the G. This is saying that you are doing nothing. Okay? So this is an abstract way of saying, so there is a way of rewriting everything in a way that will say that beta is the tensor product of the rho and an isometry. Okay? That's the first. So once we understand that the really relevant guy is rho, now I will make assumptions on rho. And the good news is rho is defined in a larger space. So second, I can split, I said for V, yeah. I can split as the direct sum of, let's call it Bi, finitely many spaces, B sub I closed, and we have functions chi I from A into R, which are the Lyapunov exponents, in a sense, the eigenfunctions, and with the property, when I do rho A of Bi, this is E to the chi I of A times nose of B for every A in A, for every I, for every B in Bi. Okay, so on these Bi's and for this diagonal guy, we get that this is just this homotety. So these are the Lyapunov exponents for this rho. So you have to think of this as some sort of oscillated decomposition for this Banach space, and rho is actually the hyperbolic dynamics, and we are having this in a very strong form. Okay? You can weaken all this here. You can make an assumption where this is only happening asymptotically eventually if you want. For the applications we were getting, that's good enough. Then there is, well, gamma is inside SL and R, so let me just put it separately if you want to do it for a little bit more general situation. 3 means that the word length on gamma and the distance in G coming from in gamma coming from G are quasi-isometric. Okay, so this is a condition which is not a condition because it's always true, but let me clarify it, what it means. So you define the word length. So what? You pick first S, yeah, I guess, inside gamma such that it's a generating set, is finite, and you define the word length as equal to this as being the infimum of the n such that there exists gamma 1 up to gamma n is S, which gamma is gamma 1 times gamma n. Okay, that's the word length. You assume S is symmetric just to make your life simpler. You don't need to assume S is symmetric. So if it is generator, it is generator.
And you're assuming higher n.
Now, to make its definition, I just need this guy to be finitely generated. And yes, I need higher rank to make sure that every lattice is finitely generated. But yeah, that's the standard definition for finitely generated groups. And a generator, so here is this notion of being quasi-isometric, and the whole point is that when you move this generating set, you will get different sort of norms, but all of them will be quasi-isometric one to each other. So the distance S from gamma to eta is word length of gamma eta inverse. So you use this word length as a norm in a sense. And then you take d sub G left invariant metric for distance on G. Any one is essentially will do the same job for us. And the claim is there exists constant C1 and C2 such positive such that the word length distance between gamma and eta is smaller than C1, the G distance between gamma and eta plus C2, and is larger than 1 over C1 distance minus C2. So if C2 were 0, then this just means that these guys are Lipschitz equivalent, that the two distances are Lipschitz equivalent. So if we are allowing C2 be non-zero, it means that in the long scale, in the large scale, they look like Lipschitz equivalent. In the micro scale, certainly could be completely different one from each other. But the whole point is that this, since gamma is a lattice, is totally disconnected, so it's discrete, the topology. So certainly in the small scale, it's meaningless. So it's only meaningful in the really large scale. And as I said, so this third condition, this is a theorem by Eskin, Lubotzky-Raghunathan, and Moses, that says that in this case, n at least 3, this is always true. And gamma lattice, this is always true. So it's a very non-trivial theorem, but it's always true. It is very non-true. So this is, I guess, important. And it's a good exercise to see why. So I will leave it for you. That if you take SL to R, SL to Z inside SL to R, this does not satisfy this quasi-isometric. So the word length in SL to Z is not the same as the distance function in SL to R. So this is really very, very different. And the guilty ones, as always happens, are these guys. This guy has distance to the origin in SL to R log n, but in SL to Z, the distance is n. And so there is no way these two numbers are linear one in each other. Okay, so this is the third condition, which allows us to swap from work length to the actual Riemannian distance on the group G. And there is a fourth condition, which we have seen it already happening. We have used it already into proving something about entropies. Let me write it here. So let me remind you here that G has this writing KAN. I'm reminding it mostly because, as you may see, the three conditions, the only thing I care is that A is abelian, that G has this decomposition into a K, an A, and an N. And of course, I will need some property of N being normalized by A, and the fact that K is compact. Actually, I will need a little bit better than K is compact. I will need the lower triangular here type of game. So this sort of stable versus unstables, and this root space decomposition. But that's all I need. So I don't actually need the SLNR property. Okay? So we have the roots of G. So we want to have the roots. Remember, they are in this SLNR situation. These are these Eij of t equals to ti minus tj. Okay, so now the fourth condition is the following. If you take all the union of, this is root spaces associated to root R over, and here I will non-resonant R. I will explain what the meaning of non-resonant is, the same meaning as we used a couple of months ago. This generates G. Okay, actually if you take all these vector fields here, you take the Lie algebra, this generates G. So this is equivalent, if you want, to make this statement, which is that I take the group generated by all these guys, I take the closure, and this is the group G. So maybe the connected component of G, if G were not connected, SLNR is connected, so I don't care. So here we say R is resonant if there exists C positive and some I such that R equals to wait a second. Yeah, doesn't matter, I guess. So a root is resonant if it is a positive multiple of one of these chi i's that we have there, and is non-resonant otherwise. So we need to have enough non-resonant roots so that they generate the group. So remember that we use also this having a lot of non-resonant roots, improving invariance of measures and blah, blah, blah. And there is a fifth condition, which says that all chi i's are not zero. So I don't want chi I, any of the chi I being zero. I don't want any of these vector spaces to be isometric. Okay? So this one should be able to, actually both 4 and 5, one is more or less supposed to be able to remove, but we are working on it. And these are all the conditions. Okay? So as I said, in SLNR, yeah, maybe some observations. So in SLNR, 3 is automatic. If you have that this row is a very particular guy, which means that it's in a sense finite dimensional representation, then it comes from the theory of finite dimensional representations. So this is automatic as well, not this, but the second guy is automatic when you come from a finite dimensional business. And in this case, 5 implies 4. That's somewhat non-trivial to prove, but 5 will imply 4. So this is what happens in finite dimension. And then the theorem says if B and beta are as above, then H1 gamma B beta is 0. So this cohomology vanish, i.e. if phi goes from gamma into B and phi of G1, G2 equals to beta G2 phi G1 plus phi G2, then there exists a nu in B such that phi of G is U minus beta G of U for every G gamma. Okay, so that's the main theorem.
And you expect gamma and G to be sort of like, in general, things that would satisfy Zimmer type.
Yeah, so Yes, let me comment on this. So, in the case of Zimmer, so this property, well, this property, if you want, automatically implies that the rank of the group, so the dimension of A, has to be strictly larger than 1. Because if you are in 1 dimension, any two linear functionals are proportional. And then that's it. So you will have, so these chi I are essentially numbers. I have the positive ones and the negative ones. And then roots will also be numbers because this is 1-dimensional. And so the positive roots will be proportional to the positive guys here, and the negative roots will be proportional to the negative guys. So in any event, you will never be able to generate all G. Even if you have all chi I are positive, so you will never get the positive roots coming here. So you will have here the span of the negative roots, which is the stable group, essentially, and that's it. This span here will be just the stable group, not all of G. So this implies that, so 4 tells you that you need high rank.
Not only for G, but also for all its factors, if it has factors.
No. So maybe yes, but no. So you can apply this theorem for gamma inside SL to R cross SL to R. That's no problem. Of course, you will need to have the right properties. In principle, it could be even gamma times gamma in SL to R cross SL to R. So a priori, there is no harm on even such type of assumption. Okay. So, of course, then it comes to satisfying all the conditions. So, which will, I didn't do the exercise. What happens if I'm taking gamma equals to gamma naught square inside SL to R square? Say gamma naught is a surface group, genus 2 surface group. Then the quasi-isometric is perfect because co-compact implies quasi-isometric. That's the most standard situation. Then for the representation rho, you can take whichever representation that comes from SL to R. Then what is beta? Well, the simplest way of defining the beta was the way I did the example before. And then the big question, so this, it's okay, you can assume that you have this. This is for rho, so this is happening always, and you want to assume all these chi I are not 0. So this puts some restriction on the representation, but it's a very weak restriction on the representation. So this is automatic. And then, of course, you have this root problem that you will need to check. So that's a little bit less obvious. So I should think about it. I honestly never thought about it. But yeah, there is no harm in what is the group. So it really can be SL2R cross SL2R without any problem at all. And certainly you can even go and be happier if you use other guys or things like that, where N and M are large. These are product of 2 rank 1, but the good news is that this has a lot of roots. So, which means that, yeah, maybe you have one of them is proportional, but you have all the other roots. And then you may be lucky, maybe not, who knows. So maybe, yeah, because here the roots, of course, all have the, no, yeah, I'm sorry, I take it back, because here the roots, in this case, well, you still may be lucky, but it's still not trivial because once one is, so here all the roots are proportional. Not all of them, but all the ones coming from this factor, they are all proportional to each other. And so then once you have one chi which is proportional to one of the roots, then it will be proportional to all the others. And then you are missing this guy, and there is no way you make up. So yeah, the assumption when you are here being product of rank 1 guys, let's say they are all rank 1, just to make the analysis trivial. So then this statement is equivalent to asking that there is no resonant root at all. So one resonant root will destroy the theory. So you just want no resonant root at all. But that's a perfectly fine situation. So there are examples where there is no resonant root at all. Okay? And then you can apply the theorem. And actually, this is pretty much the only important statement. So when you are in this rank 1 situation. So in this example, where gamma naught is co-compact, so all the other hypotheses are essentially for granted, you just want no resonant root. So the weights of the representation is not resonant with any root. Then you are safe. Okay. So, guess time is up. Yeah. I didn't expect really to write down the proof of this. I just want to tell you that the whole point is that you should not be surprising on this assumption. The philosophy of the proof is very much in the line of what we did for the corresponding theorem for invariant measures. Okay, so you play the same type of game. So you gain some. So what was the philosophy for the measures is you prove some invariance along these root directions, and then if you have enough root directions along which you are invariant, you are fully G invariant. Now here, who has to be G invariant or root invariant? Well, it's actually not fully. G is U. So you solve this equation. The whole point is that you go and solve this equation. But even though it may seem silly, you sort of solve it as a function of gamma. Okay? With some criterion. So you do some work there. And you solve it this way, this guy, but now you start playing invariance, and the way you solve it, you first show that you do some inducing from gamma to G and some cocycles up there. So let's say you do something of this sort, and then you show that U of AG is for every A in A. That's the first thing you show. Second thing you show is that U of G for every P belonging to some non-resonant root direction. So that's the sort of invariant I was talking about. And then the set of all non-resonant root directions generate the whole guy, which means that this function, after all, is constant. Now, the slight problem is that this function, as U of G, is not continuous function on G, it's only measurable function on G. So you have really to discuss some sort of ergodicity property. And that's it. So once you have that this function is constant, then you are allowed to erase this guy from here, this guy from here, and you got the solution. And you are done. So well, actually what you show is that this is true G almost everywhere, but then you play some game and this is continuous, and you have the inequality everywhere. Yet, as I said, this comes from some inducing, so this statement I'm doing here is not for the original phi and beta, it's from some guy induced on the corresponding G extension. So you just play the same games we were playing during the whole course, and you pretty much do the same. So, okay, that's it. So this was the course. Thank you for being here all this semester. Okay, and yeah, I will see you all, hopefully in person. The sooner the better, but yeah, probably next semester in person. Bye-bye.